In this video, I'm going to discuss datums. So in the ASME standard, this section is number 7, and it's called Datum Reference Frame, not how to use datums. The reason is that the datum reference frame is really important to understand. It also is fairly simple. It's really just another word for Cartesian coordinate system. So in the Cartesian coordinate system, you have x, y, and z. They're normally represented by lines going in totally opposite directions. They're 180 degrees from each other. They're 90 degrees from each other. Now, in GD&T, our datum reference frame is represented by 3 mutually perpendicular planes. Now, theoretically, they're perfect. They're exactly 90 degrees apart. In reality, they're not, and we'll at some point talk about how we square the circle with that, theoretical and what you can actually inspect. Now, our datum reference frame looks like so. We have one direction in x, another direction in y, another direction in z. This is our 3 dimensions, and it's what we usually need to measure parts. If parts are really, really thin, like sheet metal, sometimes you only need to worry about 2 dimensions, the x and the y. Now, there's another concept called degrees of freedom. This is really important for inspection. It is the order in which you constrain the feature so that the feature doesn't move around on you while you're inspecting. Let me show you how it works. So I've got this part drawn on the board. We've identified this bottom surface as datum A. This surface is datum B, and this surface is datum C. We want to set the part up for inspection, right? You can't just guess. You can't just put it down and measure from wherever. The instructions are given right here. These are our datum references, and this is the order of precedence. So it's saying make maximum contact with A, and then B, and then C. And those, when we do it in that order, they're going to take away the degrees of freedom in the order the designer intended. So if I take this surface and I put it up against my whiteboard, I've taken away degrees of freedom. Now, which ones? Well, we can move the block around, right? But we want to know where we can't move it. So if it's on the board, it can't move like this, and it cannot move like this, and it can't move in and out anymore. So we've taken away the translational degree of freedom in Z. We've taken away 2 rotational degrees of freedom, both V and U. Now, you almost never have to use the U, V, and W. I put them up here. They're just the rotational degrees of freedom. So we've taken away 3 degrees of freedom with our first datum reference, datum A. Datum B, we're going to, while it's constrained to datum A, constrain it to another surface. If you notice, you can hear it, 1, 2 points of contact. It's got to be a minimum of 2. It can be more than 2. But what we've done, when I'm just pushing it up against the bottom of my board here, we've taken away another degree of freedom. We've taken away Y, because it can't move up and down anymore if it's stuck to the bottom. And then we've taken away a rotational degree of freedom, and then it cannot move like this. Okay? The last is datum C, which is going to be this side right here. And I actually drew my angle plate on the wrong side, so let me draw it again. So we're going to push it up against something. On an open inspection, a lot of times it'll be something like an angle plate. Now, it only needs to make 1 point of contact with the angle plate. The reason being, it's only controlling 1 degree of freedom, just the translation. To stop it from moving left and right, you only need 1 point to achieve that. At this point, we've constrained this part in all 6 degrees of freedom. We have to do that for location and profile that controls location. So in order to measure the location of these holes, the part has to be fully fixtured, right? It can't move. So when we go to measure the holes, all of the measurements are going to come from this bottom corner, right? Because we've got a datum here, got a datum on the angle plate, and we've got the board. Okay, so everything is in reference to that bottom corner. That's the 0, 0, 0 of this part. Now, it doesn't have to be that way. It depends what order the datums are put in here, and it doesn't have to be flat planes. Datums can be features of size. So a datum could be an axis, or it could be a center plane, right? Remember, datum is a theoretical point, line, or plane. So the line could come from a cylinder. The plane could come from two real planes to make a datum in the middle of the part. Let me show you what that looks like. Now, I've identified datum B as a center plane. What this is saying is that the center of this part is where the measurements need to come from. So we've moved the origin from one side of the part to the center of the part. This is really common in symmetric features where you don't favor one side or the other. The way this is supposed to be inspected is you have some kind of centering vise that grabs it, and then you can find the 0 and measure out from there. Another thing I want to mention is that when your datum is a feature of size, it does have a material condition, just like any other feature of size. So in this case, datum B is shown here. It applies it regardless of feature size. Datums A and C do not. They're planes. They don't have size. They're not features of size. But datum B could have the MMC modifier. That way, when you go to inspect it, you don't need that expensive centering vise. You could just set two angle plates 2.02 inches away, so the MMC of that feature or the virtual condition if it applies, and then measure from the center of those two angle plates. The part could move around between them. Okay? It's a little bit more complicated to set up, but what it allows you to do is have something like a robot check parts for you, because now you have fixed gauging. You don't have to center the vise and then find the middle. Okay? One thing I want to mention when we do use the MMC, so what it's known as when it's used the datum reference is MMB, maximum material boundary. You can still check it as if it's RFS. That's totally fine. RFS is always a more stringent call out than MMC. So anything that says MMC, you check it as if it's RFS and it passes, you're good. It's only when the piece fails that you might need to go back and account for the MMC or the MMB. The next concept I want to talk about is true geometric counterpart. This is kind of like actual mating envelope, but for datums. So all the true geometric counterpart is a perfect shape that's the opposite of the datum. So if your datum is a flat plane on the part, the datum simulator is a perfect flat plane that touches it. If your datum is an external cylinder, the datum is an internal cylinder that collapses onto that external cylinder. So imagine a collet or a chuck squeezing onto something. That would establish the axis of that cylindrical datum. True geometric counterparts are used or simulated with datum feature simulators. Okay, so just inspection equipment. Or if you're using a CMM, the computer code in the CMM will just figure it out for you. Now I want to talk about some of the ways datums are identified on the drawing. If I didn't go through it before, the terminology with this, a datum is a perfect line, point, or plane. A datum feature is a physical portion of the part. So this plane is our datum feature. Datum feature symbol is this little guy. So the letter in a box with a little triangle pointed to something. It tells you which feature is a datum. The datum reference is in the feature control frame, tells you what order to use your datums and at what material condition the datums apply. And then the datum feature simulator is just your inspection equipment. So a surface plate for a regular surface datum, or a mandrel if you have an internal datum, so an internal hole. You could use a mandrel to expand and capture that. Gauge pins also work. The largest gauge pin is the feature simulator for a lot of holes up to about 1 inch. So let's go into some of the ways datums are shown on drawings. The first example I have here, our datum feature symbol is attached to the extension line, but it's not in line with the dimension. The datum feature symbol could just as easily be attached directly to the part surface. That would do the same thing. It just cannot be in line with the dimension. The reason being is that if you do that, as in this example, it means that the datum is the center plane of this feature, not a surface. So in this example, this surface is the datum. In this example, the datum is in the middle of the part. Inspection-wise, you have to tackle that in a different way. Neither side of the part is more important than the other. Now, I recommend if you're making drawings and you want it to be a surface datum, take your datum feature simulator, take your datum feature symbol and just flip it upside down. That way there's no guesswork involved, right? Often when you're changing drawings, things can kind of just move on you. You don't want a situation where the datum is really close and you're not sure whether the designer meant for it to be a center plane datum or they meant to be a surface datum. Another giveaway is there should be a center line going through this part because it's symmetric if the datum is the center plane of the part. Next up, when it's a datum is a cylinder, so I have 2 diameters here, one of which has a plus or minus dimension and the datum feature symbol in line with the dimension. That means the axis of this diameter is the datum. You're comparing the axis of any other diameters to that diameter. Okay? Now, you often have feature control frames on your datum features. So I've given a couple examples here. Flatness could have the datum feature symbol attached to the feature control frame. Just indicates that this surface is the datum. Here's a flatness applied to a derived median plane. Okay, so this has a datum symbol attached to it. It means that this is the datum. With a cylindrical feature, we've got a feature control frame. Normally, right here, you wouldn't put the datum feature symbol on the feature control frame because it'd get in the way of the dimension line. So you would do what I did right here, move the dimension totally out of the way and then put the feature control frame on it. Now I want to mention, in the 1994 standard, okay, you are not allowed to put a datum feature symbol on a feature control frame unless it applied to a feature of size. So any drawing made to that standard, if you saw a datum feature symbol on a feature control frame, you could assume it was a feature of size. It's not that way anymore. In 2009 and 2018, you can put the datum feature symbol on any feature control frame. So this applies to a surface. This applies to a feature of size. It's kind of a free-for-all. I personally like the old way a little bit more because it made drawings slightly quicker to read, because if you saw datum feature symbol on a feature control frame, you already knew it was a feature of size without having to do any more looking. But rules change. Now, I want to take a look at a couple other types of datums. The planes and cylinders are the most common. Okay, almost, most parts you can get away with either a surface plane, center plane, or the axis of an internal or external cylinder for a lot of your datums. But it's also somewhat common to see threads called out as datum features. So in this example, I've got a thread and then a diameter that's positioned to the thread. If the thread is what is controlling everything in that part, then it should be the datum if it's the most important thing. In this case, there's a whole lot more length for the thread to grab onto than there is for this diameter, so it makes sense as a datum feature. Now, the tricky part is that when you go to inspect this, unless otherwise specified, the datum is the pitch cylinder, which is an imaginary thing in between the top and the bottoms of the threads. This requires expensive inspection equipment to capture, depending on the thread size. But it is the most functional because that is what's going to locate the thread at assembly. Normally, if a thread is the primary datum, there won't be a feature control frame attached to it, so no straightness or anything. The reason being that threads have their own tolerances already, so you don't need to control the form of a thread, so no need for a straightness tolerance. The datum feature symbol is just attached to the bent portion of the leader. Now, an option for designers is to identify the major diameter for external thread or the minor diameter for internal thread as the datum. So it would look like this. This tells the inspector that they don't need to find the pitch cylinder. They can just take the outside diameter of the thread and use that to simulate the datum. So they could just put the thread in a V block and they're done, right? It's easy enough, preferably a collet or something, but they could treat it just like any other diameter. It's not special in any way, really. The downside, design-wise, is that the major diameter doesn't locate the thread as good as a pitch cylinder, so you wouldn't want to do this if it's really critical to locate something. I mean, you really shouldn't use threads to locate things, but I guess it just depends on the stack up you're looking at. This could induce error at assembly that's difficult to keep track of. Right? So next, you can use profile shapes as a datum. So what I'm talking about are irregular features. So in this case, I've got a slot shape that's an external feature. So it's a, what do you call it? So it's a slot shape with 3 holes going through it. You could pick, this side or this side to favor and make one of those a datum, or you could, tolerance the outside of this with a profile, and I should have a all-around symbol there. Dimension it with basic dimensions. I left that part out, and make that the datum. This is allowed. So that takes away 5 degrees of freedom, right? Because it's a special shape. It can't move in any direction except up and down. So datum B is one of the top or the bottom of this part that locks down the last degree of translation. You probably wouldn't want to specify this as RMB or RFS though. The reason being, what you're telling the inspector, if you do this as a primary datum, in order to have a true geometric counterpart at RMB, you'd have to have a perfect opposite shape, so an internal slot that collapses at the same time to catch the high points. That kind of stuff is possible to produce for inspection, but generally, unless you have a really good reason not to, you want to specify that at MMC or MMB so that they could, make a slot shape, drop it in there, and then check the position as normal. Okay, so basically the part can rattle around a little bit. I have another video about that. I'll put a title card up. Now, you can also do this with like a cone shape if you apply a profile to it, and that would lock down even more degrees of freedom. But using these as primary datums, I would warn against it unless you have a really good reason, or if your company has CMM machines that can just figure it out for you. This kind of stuff could be very difficult to inspect on open inspection with height gauges and whatnot. So next up is using a pattern of features as a datum. This is common, and it's a good way to establish that the pattern is important and then everything around it is less important. So here we've got 4 holes that are positioned to datum A. We have to use position because they're a pattern. Perpendicularity wouldn't have anything to say about how far the holes are from each other. We need to use position for this application. So position, diameter 30 thousandths MMC to datum A, but this pattern establishes datum B. And then all of the other features of the part are going to be relative to the pattern. Now the tricky thing with the pattern is that none of the holes individually is the origin for measurements. The origin is actually in the middle of the part, right? So that pattern creates an axis in the middle of the part, or you could think of it as 2 planes in the middle of the part. You essentially are going to measure from the center of those 4 holes. Again, on a CMM, this is super easy. On a plate, you basically have to have this set at MMC. The reason, when we look at this center hole, right, we're going to position it to datum A and that pattern of holes. If you called that out at RMB or RFS, you would have to have 4 pins that expand at the exact same time, that are perfectly located, so at least gauge maker's tolerances. They all expand to capture the part until it stops wiggling. That can be done, and they do make fixtures and gauges for that. But if at all possible, if you can use the MMC modifier, it's possible that you could have fixed gauging for that. So you could have a robot drop the plate on 4 pins. If it fits, it could check the next thing, you're good to go. At worst case, you could check it with a CMM machine, and the MMC just gives you extra datum shift if you need it. So this outside right here has a profile to the same datums, A, B, and MMC. This is great if the outside of the part mates to air, which just means that there's nothing it's going to touch at assembly. So you could think of the outside of a television screen mates to air. A lot of things mate to air, and you want to be sure to give that kind of stuff as much tolerance as possible because it's not functionally very important. The last thing I want to talk about are multiple datum reference frames. So the example I give here, we've got 2 holes in a long bar. So let's say this bar is 5 feet long, okay? So we're going to measure the location of the holes. If we use a traditional dimensioning scheme, we've got A as the large surface here, we've got B as the long side, and C as one of the ends. So we go set up to inspect, no big deal for this hole. For the one that's 5 feet away, so we're measuring from datum C to find this location, we're going to have difficulty getting inspection equipment that is accurate enough that can span that far. Also, it depends on the function, right? If this hole does something over here and this hole does something over here and they don't really work together, we can separate them tolerancing-wise. So what we're going to do, instead of both of them using the same ABC datum reference frame, as we talked about before, the ABC is how you set it up for inspection. A first, B second, C third. All your measurements would come from this corner right here. Let's add another datum. So we're going to add datum D, which we're going to establish as this side of the part. We need to have a tolerance for that datum because we're using basic dimensions. We need a profile to establish the location of that surface from this side. So that profile is going to be to A, B, and C. So we're still going to have to measure that to make sure that's within tolerance. that comes and makes datum D. Now this hole can be measured from A, B, D, from this side. So inspection-wise, it can be a little bit easier depending how you set it up. Functionally, this could help as well. If this hole is just sliding over something that has to do with one edge, it would be the same over here. You're measuring from the edge of the important side, not the total other side of the part. Okay? Whenever you do this, though, you're going to introduce extra tolerance stack up whenever you have multiple datum reference frames. It also causes inspectors to have to set up differently, right? So this is a different datum reference frame than this. It requires a different inspection setup to make that happen. If you're programming a CMM, probably a little bit easier, but you still have to remember to punch in the right stuff. So that's it for this first talk about datums. I'll probably do another longer video about this soon. Datums is a huge topic. There's a lot to cover. I think this is good enough to get everybody started. So if you enjoyed the video, please like and subscribe. Leave a comment down below.